In clinical imaging, the difference between a non-diagnostic blur and pinpoint anatomical clarity is a matter of strict physics. You cannot simply turn a dial to increase image quality. CT imaging is a rigid mathematical optimization problem governed by three physical pillars: resolution, noise, and contrast. Every CT scan is constructed from millions of tiny, three-dimensional building blocks called voxels. The physical dimensions of this single unit determine the absolute limit of what you can see. A voxel is defined by two intersecting planes. First, the transaxial resolution in the XY plane, the cross-section of the patient. Second, the Z sensitivity, which stretches along the longitudinal axis of the patient. When these dimensions align perfectly, they form an isotropic voxel, a symmetrical cube. This exact geometric symmetry is the required standard for accurate, distortion-free 3D medical reconstruction. To master clinical CT quality, we have to look at the scanner hardware and the quantum physics required to shape that microscopic cube. Inside the CT gantry, the transaxial plane is captured as the X-ray beam originates from a focal spot, projecting through the patient to strike a curved detector array. The physical size of this focal spot sets a hard baseline for maximum spatial resolution, but an intense stream of electrons hitting a tiny focal spot generates massive heat. Using the fine spot severely limits the maximum tube current safely applied before causing thermal damage to the anode. The diverging X-ray beam projects the detector's physical width onto the bore's center, the isocenter, dictating the minimum gap to distinguish objects. Engineers bypass this using a flying focal spot. By rapidly shifting its position, the system multiplies projection samples, significantly tightening in-plane resolution. Similarly, the detector array itself is intentionally offset from the center of rotation by exactly 1/4 the width of a single detector. As the gantry completes a 180-degree rotation, this misalignment forces an interleaved sampling pattern to capture even more data points. These rigid geometric boundaries and hardware tricks dictate the absolute ceiling of spatial detail before digital software reconstruction even begins. Once the physical data is collected, control shifts to the digital reconstruction matrix, where user-selected parameters shape the final image. In the pixel size equation, pixel size equals the field of view divided by the matrix size. By retrospectively processing raw data into a smaller field of view, the pixels shrink, isolating minute anatomical structures with sharp clarity. This relationship is governed by the Nyquist limit. Capturing a high maximum spatial frequency, the ability to resolve incredibly fine, closely packed structures, requires proportionally smaller pixels to display it. Software can mathematically subdivide the grid, but it cannot extract high spatial frequencies that violate the Nyquist limit. The math is absolute. Now we rotate our frame of reference 90 degrees to look down the longitudinal axis of the patient. This introduces Z sensitivity, the effective thickness of the imaged slice. Slice thickness is dictated by the physical width of the detector rows and the spiral pitch of the scanner. Using a spiral pitch of less than 1 creates overlapping data samples, allowing us to reconstruct very thin slices. This demonstrates the partial volume effect. A thick imaging slice envelops adjacent, distinct tissues and averages their attenuation values into a single, inaccurate shade of gray. Slicing that exact same physical space into thinner sections eliminates this mathematical averaging, restoring diagnostic accuracy. When you match that thin Z-axis slice to the tiny XY pixels of the transaxial plane, you create the isotropic voxel, a perfect mathematical cube. Securing this isotropic cube is a clinical necessity, allowing radiologists to perform 3D multiplanar reformatting without introducing any structural distortion. We evaluate the success of this geometry using a completely uniform substance, like a water phantom. This introduces the primary antagonist of image quality, noise. When scanning a uniform liquid, pixels do not display a solid tone. They constantly fluctuate in their Hounsfield values due to quantum noise, a stochastic process caused by the random statistical nature of X-ray photons striking the detectors. This noise variation follows an inverse square root law. To reduce the visible noise in an image by half, you cannot simply double the photon flux. You must quadruple the total number of incoming photons. An operator has 3 levers to increase that photon count: double the tube current, double the rotation time, or double the physical slice thickness. Any physical attempt to aggressively suppress quantum noise inherently demands a massive exponential increase in the radiation dose delivered to the patient. The physics of the CT scanner forces a zero-sum trade-off between geometric resolution and photon statistics. Slicing a volume thinner to improve your Z sensitivity means a smaller detector area is exposed. Mathematically, far fewer photons hit each specific slice, driving quantum noise sharply up. The digital reconstruction faces the exact same penalty. Applying a sharp mathematical kernel preserves the high spatial frequencies needed to see fine bone detail, but it fails to average out stochastic signals. The resulting image is sharp but highly noisy compared to soft tissue reconstructions. Pushing spatial resolution toward perfection automatically starves the voxel of photons, degrading the image with noise. The third pillar of image quality is contrast, our ability to clearly differentiate adjacent biological structures from one another. This separation relies on the inherent differences in the linear attenuation coefficients of tissues. However, pushing a higher beam energy through the patient to increase photon penetration generally reduces the contrast between those objects. When inherent tissue properties are too radiographically similar to separate, like blood vessels and surrounding muscle, artificial contrast media is introduced to force a measurable difference. Look at this diagram of the diagnostic triangle. Resolution, noise, and contrast are permanently tethered. Moving your protocol closer to one node mathematically pulls your image quality away from the others. True mastery of CT physics means balancing this equation for every specific clinical question. It requires securing just enough photon statistics to overcome the stochastic noise floor, capturing diagnostic resolution while strictly minimizing patient radiation.